Monday, Tuesday, then Thursday, Friday.
Yeah, so if you go to the register website, there's an exam schedule. So ours is going to be Thursday the 9th at 9 a.m. So what I'm going to do is I'm going to give you the exam on Monday. I'll send it to you by email. It's going to be a take-home exam. And then Thursday at 9 a.m., we can meet here if you have questions for the exam. So we'll meet here, and if you don't have any questions or anything, you can just send me your email me your exam, or you can give me your paper copy sometime before. So if you don't have to be here, if this is your last class and you don't have to be on campus anymore, you can just email me your exam. That's fine. Huh? Oh.
I was hoping that I'd be able to go.
And then well, we can talk about this later, but Tuesday is going to be your electronics exam. No. Yeah, it's the if I give you a problem like the one with inductors and capacitors and ask you to solve. I mean, you can do two in a couple hours. It's just they're very long problems. So. And I want to add you some simulations and stuff like that. So it's better to do it at home. To do it, take an exam. Yeah.
All mine are on Wednesday through Friday. So Monday, Tuesday.
Okay. That's awesome. Yeah. I don't know. Yeah, so that way nobody's gonna scare. Okay. You guys have some
Yes.
questions?
There's a hodgepodge.
Oh, I know I did 25. You don't even need to look at it.
I want like to be fully
Yeah,
I really,
I just
really
a
try.
Recording function for. Okay, so I'm putting it. So I showed you this a couple of weeks ago. That is was, but it was I had a battery, and then you apply the battery, and then what we have here is this coil. I'm going to show it to the people on the website. You have the coil, and then when you have the coil and you have this current going through the coil, so if you have a current inside a magnetic field, you have an you're going to have a force. And because the location of the coils, you create a torque, and then the torque creates this motor to start rotating. And that's basically the principles of any. What happened? Holy crap! How many pages you have?
Let's just say problem two took a lot of attempts.
Okay.
Before I think I got the
What
right.
we saw is that, okay, if you have that current going through the wire, and you have that current inside a magnetic field, you create a force,
And that force is just allocated to the coils, to the torque, and then you see that motor rotate. And that's basically the principle of any electric engine. So whether you have a blender, and basically you have something like this in the blender, or if you have a Tesla, you have something like this in the Tesla. Okay? So all electric motors kind of work on that same principle. Now, we can do the opposite too. Like if we have a wire, in the wire we have a lot of free charge, we have a lot of free electrons that can move. And if we rotate this thing, we have a charge that is moving inside a magnetic field. And then the consequence is what is going to happen is that you're going to produce an electric potential. So the same way that the electric potential makes this motion, if you provide the motion, you're going to create an electric potential. So I don't know if you can see it. You can get close. You can see the numbers. And if I rotate this thing, you can see that number is going to jump. Okay? This is a DC voltage, this is a direct current. And if I rotate to the opposite side, you can see the voltage to be the opposite number. I don't know exactly if it's possible or not, but it's positive a zero of this. Okay? Now, the voltage is very small because, well, whatever I can rotate is very small. So, but if you have these going through a waterfall, and you have these moving through constant force, water, you're going to produce a big amount of power. If you have wind, if you have a couple fan, and you have wind blowing to this and it's moving, then you're going to create this constant electric energy. So if you provide voltage, you create these motors that are moving and that consume energy, like the motors in the blenders or your car or whatever. If you have the other way around, if you have the wind or the water or something moving, you are basically having a generator. And it's basically the same thing. Okay? So that's one of the applications of electromagnetism. Now, you can do the same. So the motion is relative, right? So right now I'm moving the wires, but if I have coils fixed, and here I have a magnet, and I move the magnet, and the coils remain fixed, will be exactly the same thing. Okay? So I can either move the magnet and remain the wires fixed, or I can leave the magnet fixed and move the magnet. Okay? So the first person that noticed that was a name named Ørsted. And Ørsted, what he says is that, okay, we can have an electric field or a moving magnetic field produces an electric potential or produces an electric field. Okay, and the way he said is like he put in an equation, and that equation is basically, okay, we're going to have this electric field across our circuit, and this is going to create a magnetic field that changes in time, ds. Okay, I'm going to apply Stokes' theorem to the left side. So applying Stokes' theorem. Yeah. And by now you should know Stokes' theorem by heart. But of course, I'm going to write it down just to make sure that you remember. So Stokes' theorem
basically says that we can replace this line integral by a divergence across an area. Okay, so if I substitute this cross product, this divergence, this curve of the electric field on my first equation, then I'm going to have okay, so we can get rid of the integrals because they're basically integrating over the same surface. So I end up with this. Okay, and this is the finding of Ørsted. If we have a magnetic field that is changing in time, it's going to produce an electric field. Okay, now notice that this is in opposition. This contradicts what we knew or what we know about conservative electric fields. So at one point we did this exercise that all electric fields have to be equal to zero, and we use this as a proof to find out if a vector field was an electric field. And basically we did this proof. And if we got something different than zero, we say like, well, this electric field is not conservative, so this cannot be an electric field. And notice that this is completely opposite to what we have now. And the difference is that when you have a moving magnetic field, it's going to produce an electric field that is not conservative. Okay? Okay. So I'm gonna, just remember this equation. I'm gonna write it again, but this is kind of like a big deal. Okay, this is the third Maxwell equation, and this is gonna be the Maxwell equation with varying fields. So this is Maxwell equation. Time varying field.
So, this may be a dumb question, but I'm going to try it. What if the right side is a constant, like it's a constant and gets put in, so then it's partially derived from zero? So you need to have a moving magnetic field, a magnetic field that changes in time in order to produce that electric potential, that electric field. If the magnetic field doesn't change, it's not going to produce an electric field. Okay? Now, what we had before was Maxwell equations for static fields. So when we have a static magnetic field and when we have a static electric field, we have these Maxwell equations that we have these guys over here. Okay, we have these. These are the static field Maxwell equation. Okay, what we try to do now is, okay, what happens with Maxwell equations once once we don't have these constant fields? What happens when we have a moving magnetic field? So when I say moving, I mean a magnetic field that changes with time. So what happens when we have a moving magnetic field? What happens when we have a moving electric field? How does these equations change? Or maybe they don't change, maybe remain the same. So that's what we're trying to do now, okay? So what Ørsted found out is, okay, if you have a moving field, a moving magnetic field, what's going to happen is that you're going to produce an electric field.
So this third equation changes to this. Okay, so this is the time varying Maxwell equation. Okay. Now the other one that we need to modify is going to be the last Maxwell equation. That's the one we're gonna change, and in order to change that one, it's gonna take a little bit of math, just a little. Okay. I'm gonna start with a definition, and that definition is that the divergence of the current is basically going to be a change in charge density with respect of time. And here's a negative over here. Okay. The other definition that I need is Ohm's law. And Ohm's law are going to say that this is going to be my current density, and this is going to be the conductivity of the material. And this E is going to be the electric fields. The Ohm's law that we are familiar is something like this: voltage equals the resistance times the current. The originally Ohm's law is expressed like this, but when you calculate the current going through a wire and calculating the resistivity of the wire and the electric potential caused by that, you end up with the one that we're more familiar with. But this is the original Ohm's law. So we're going to have this definition over here, and we have that one over here. Okay. Now, going to Gauss' law. Okay, and we know that Gauss' law is just going to be this divergence of the electric field. And what I'm going to do is what I'm going to do. Okay, I'm going to substitute. I'm going to call this 1, this is 2, and this is 3. So I'm going to substitute equation 2 into 1. And that's going to be okay. I also know that if I compare this equation, I'm going to call it 4. So if I look at the left side of equation 4, it's very similar to equation number 3. Is the only difference is that I have this sigma factor. So I can say that this divergence is going to be equal to sigma rho b over epsilon. Okay, so equation 4 and equation 5, they have to be equals to each other. So I'm going to have minus rho b dt is going to be equals to rho b epsilon. I'm going to put everything on one side of the equation. Well, no. What I'm going to do is what I have here is a third order differential equation. So I'm going to separate variables. So I'm going to divide by rho b, and I'm going to multiply by dt. So I'm going to have nope. I'm gonna multiply by -1. So I have and I'm gonna integrate here with respect of dv, and I'm gonna integrate with respect of t on the left side, on the right side. Here I'm gonna have natural logarithm of rho v, and here I'm gonna have minus rho v minus sigma epsilon t plus a constant. I'm gonna try to get rid of this natural logarithm. Nico and McKenna, this may look very familiar. This equation may look very, very familiar for you guys. So I'm gonna get rid of the natural logarithm. So I'm gonna have rho v equals e to the minus t c1. E to the c1 is just a constant. And tau is going to be epsilon over sigma. Maybe not. It's going to be an initial charge. Okay, so this equation over here, all these things that we have done so far, this is just an equation. Makina, do you recognize this equation?
Yeah, I recognize like the negative field of time.
The minus t minus tau. This just basically tells you the charging of a device. It went over here. Yeah, there you go. There you go. So this equation over here realize the charging of the current, how the current changes when it's charging some electronic devices. You see this equation when you're working with capacitors and when you see inductors. So when you're talking about how a capacitor charges with respect of time, you find this equation over here. Okay, we just derived this equation just based on this. So we have a current where the current changes depending on how the charge changes, which is what happens when you have a capacitor. Now, we're going to use all these things to modify that last Maxwell equation. So for Maxwell equation, I'm going to use Ampere's law. And Ampere's law, it says that the curve of H is going to be equals to J. Okay, so remember you have a wire, and the wire you have a current, and then what you're going to do is you create a loop. This loop can create a surface. You look at the current that crosses through that surface. You create that integrator around the loop, and that helps you to find that magnetic field created by the current. Okay, so I'm going to start from here. And then I'm going to take the divergence of this curve. Okay, so I take the divergence on the left side. I'm going to do the same on the right side. Okay, now on the right side, that's what we just did. We know that this is going to be equal to negative rho, the partial derivative of rho v with respect of time. So this The left side, I don't know if you recognize it, but this is a vector identity. And basically, this is a vector identity that the curl of any vector field, sorry, the divergence of the curl of any vector field is going to be equal to 0. So we end with something like that, which makes no sense. Okay? And Maxwell was one of the first ones to understand that there was inconsistency in Ampere's law. One of the reasons that Maxwell is so famous is because he corrected this equation and said, like, wait, this makes no sense. This is not possible. The example that they were trying to use is trying to find the current across a capacitor. So let's say that I have a capacitor and a wire, okay? And I want to find out the current across that capacitor, or the magnetic field across that capacitor. So I'm going to do a loop, and I'm going to define this surface here as 1. Okay? And if I do, let me make sure that I have it correct.
Yeah, that's the one before.
Yeah, and the loop is L. Okay? This is going to be equal. So the magnetic field across this loop is going to be equal to the current that goes across this surface. Okay? And we know that this is going to be the current that is enclosed. Okay? We have done these problems before and stuff like that. Now, we usually define the surface, this S1, that is kind of enclosed by the loop. And we usually pick, if the loop is going to be a circle, then the surface is also going to be kind of this disk. But the surface can have any shape that we want. Okay? So now I'm going to have the same capacitor. Okay? I'm going to create the same loop. So again, what we're trying to find out is what is the magnetic field on this loop, okay? But now my surface, I'm gonna do a little bit different. And imagine that I have like a plastic bag, like one of those supermarket plastic bags. And instead of being assigned flat, it's gonna be something like this. It's go through the aperture of the capacitor. Okay, so when I apply Ampere's law, well, the current that goes to the surface, there's no current going through this capacitor. That's one of the things that we have learned about capacitance, is that if you have a constant current, this capacitor works like an open circuit. So there's no current here. So this will be equal to 0. So it means that there's no magnetic field, but we know that there's a magnetic field because if we solve the same problem just changing that surface, we get a result. So there's an inconsistency here that people were not able to understand. How do we solve it? And Maxwell, what we did was that, well, he found this inconsistency and solved it. Okay, so we're gonna try to repeat a little bit of what Maxwell did. Okay, so what Maxwell did was he created a new variable. So he said, I'm going to modify Ampere's law, and I'm going to say that Ampere's law is going to be equals to this. And J sub D, he called that the displacement current. Displacement current density. And J, this is just the conduction current.
he basically, okay, there's an inconsistency here in Ampere's law, we need to solve it. I'm gonna assume that there's this additional current that is going there that we don't know exactly what happens. Okay, so again, I'm gonna apply the divergence of both sides of the equation. Okay, left side, we know that that's going to be 0. That's an identity. And here, I'm going to have this thing over here. Okay, we know that this part, this is what we've been working around. This is just going to be this partial derivative. Okay, so what I'm going to try to do is to solve that equation and try to find an expression for J sub D. Okay, so I'm going to have okay. And once again, I'm gonna use Gauss law. I'm gonna write it over here. And I'm gonna use Gauss law. And I know that from Gauss law, I know that the divergence of the electric displacement, that's gonna be equal to my charge density. Okay, so I'm gonna write this divergence here. So I'm gonna have I'm gonna move some factors over here. And we can see now that, oh, this displacement current, well, that's happened only when you have electric displacement that changes with time. And then we can rewrite Ampere's law. As something like this. Okay, now when you have a capacitor, the capacitor doesn't charge right away. The capacitor charges with time. So there's going to be a time that is going to be 0, and the charge starts charging slowly and slowly. So during that time, you can imagine that this current, this conduction current is 0 because there's no conduction. The current that we see in here comes from this displacement current, from this change in the displacement field. So we can try to apply, again, Ampere's law, now using these concepts over here. So if I apply Ampere's law,
So I'm doing the same problem that I showed you guys before. Oops. Which I create this loop L, but now my surface is going through the capacitor. So because there's no current, there's no conduction current going through the capacitor, then this J is going to be 0, and then I'm going to have just this thing. JD, J sub D, this is going to be the electric displacement, the change in the electric displacement with respect of time. And what is the electric displacement inside parallel plates? You just get this example about that. And you have parallel plates with charge density rho s. What is the electric displacement? What is the electric displacement inside the plates? You guys just did that. That was exam. Okay. So when you have parallel plates, the electric displacement is just going to be the charge density. Okay. So this is just going to be the charge density times a differential of area. This over here will be the charge that you have on the plates. So this d dt divided by the charge. And what is the change of charge with respect of time? It's going to be current. So at the end, we can solve what is the magnetic field created by a charging capacitor. Now, one of the things that this term is usually very small, and most of the times can be neglected. But when the electric displacement starts changing at high frequencies, then it becomes relevant. Now, when Maxwell created this correction, there was no way that they could create electric fields that changed with time. They didn't have any way to change the electric field so fast. And it was probably like 40 years after Maxwell came with these equations that Hertz created an experiment in which he was able to modify the electric field, and he was able to detect those changes in the electric field. Well, basically, what Hertz did was to create a radio transmitter, and that's where we named frequencies after Hertz. So Hertz, the reason that he's famous is because he came up with the experiment to prove Maxwell equations, specifically this equation over here. This equation over here. Okay. Cool. So what does the Maxwell equations look like now? So for the time varying we have the Gauss law, And we have like the equivalent of Gauss law for magnetic fields. And then we have the curves. We have the curve of the electric field. That's going to be changing magnetic field. And we have the curve of a magnetic field. That's going to be a current plus this changing placement. Now, the way you read these equations, especially the last two, is I say, okay, a changing magnetic field, so magnetic field that changes with time is going to create an electric field. And here is that there are two ways that you can create a magnetic field. One is with a constant current or with an electric displacement, so it's an electric field, that changes with time. Okay, so that's how you read those equations. Now, there are some other properties here that are kind of implicit. The electric displacement is going to be epsilon times the electric field. And this magnetic field is mu times B. B is mu cross H. We can rewrite this as P, and this will be mu okay, so this is when the electric and magnetic field exists inside the material. Okay, and the last thing are boundary conditions. And this one I need to see them because I never remember. So and everything we have seen in this class can be reduced to this single page. That's it. This is the whole semester. Everything. All that we have done is just to derive this equation and these boundary conditions. Yeah, you can get rid of everything else, just keep this page.
Just give it out to the next class, the first day, be like, all right.
Yeah,
dismiss.
this is it.
That's all you need.
I have a book that is like 50 pages, and it's natural equations, and it's just 50 pages, and I love that book because it just start with each one of these, describes them really fast, and then that's it. You just mention it. No exercises, no homework, no problems, nothing. It's just describing these little equations.
That's what that doesn't contain 500 pages.
It's, yeah, and it's like $20. It's super cheap, but it assumes that you already know how all these got derived. Now, yeah. If I were to teach this class, the sequence of this class, we'll use this textbook and that little teeny tiny one. Just as a reminder.
I'm just thinking, the next class I'm teaching this, we'll probably get that small textbook and be like, what the hell? Why'd you give us this little baby textbook?
Now I know. So what we're gonna be doing the next couple of days, Wednesday and Friday, is basically applying these things to looking at propagation of electromagnetic waves, which was one of the big accomplishments of Maxwell, was that he was able to produce or describe an electromagnetic wave. Now, what is interesting about this equation is that it's showing the relationship between electric fields and magnetic fields. And it basically shows that the two of them are interconnected. Okay? A moving magnetic field produces an electric field, and a moving electric field produces a magnetic field. And that was a big issue.
Just imagine Maxwell explaining everything for the first time, just having like a giant chalkboard.
So Maxwell equations, this is not the shape that Maxwell showed his equations. Maxwell equations, original Maxwell equations are like 16 or 24 equations. And it was, I think it was Ørsted, that he was like, dude, this makes no sense. Let me clean them up. And then he reviews all of them into these Maxwell equations, the boundary conditions, and this constitutive relationship.
And then he put his name on it. Still let Maxwell keep all the credit.
Maxwell, the big accomplishment of Maxwell was this guy. And this is the thing that connects everything. That's why he kept the name. But this is Gauss' law, this is Ampere's law, this is Ampere's law.
It's just like the fact we said it's Maxwell's equations.
And friends.
And friends, yeah.
I mean,
Friends
Maxwell-
keep it all
Maxwell-
the way.
Maxwell supporting cast.
Yeah. But what we're gonna look into the next couple of days is just how these apply to magnetic fields, how do we work with propagation of waves, and just specific cases. But that's it. Okay. Now, before you leave, there is the student evaluations that you should receive it on your email, phone, whatever. So make sure that you fill those before you
Is that
leave.
right now or just whenever?
You can do it now. I mean, you have 10 minutes.
Yeah, get the email.
I've been getting a
It'll
lot.
probably be in other. That's what's been in years past.
I've been getting a lot of emails today for some reason.
Yes.
It's in other. It's not in your focus.
I
Don't check focus.
I'm on your other,
Oh, okay.
yeah.
You haven't received it?
Wait.